my name is Kevin Farley. I'm here with Sunil Agarwal. We're both program managers in the SQL Server product team. So we've been working in the core of SQL Server for both of us over 10 years. We've seen a lot of change in that time. We're here to talk about in-memory OLTP. The road ahead obviously refers to the new features in SQL Server 2016, which we're just announcing. I want to set a little bit of context here about the way we're doing engineering, which is different than it's been before. How many of you people have been to one of the in-memory OLTP overview sessions? Good. So most of you have that context. I'll go briefly over that. But what I want to say, though, is we're throwing a lot of new functionality in. And the way we do engineering is fundamentally different than we've done in the past. In the past, back in the 2005 era, what we used to do is we'd open up the release at the very start, and engineers would check in all the pet projects they've been thinking of for a long time, and we'd spend the next 3 years trying to get it to a level of quality where we could actually ship. We've pivoted that around. So instead of adding all the functionality and then incrementally adding quality, we've pivoted our whole engineering system to where now the mainline SQL main is always at ship quality, and we incrementally add functionality. And then when it's time to ship, we can ship with confidence, and whatever isn't lit up in that release comes in the next one. We've been working very hard in our engineering systems over the last year plus to where now for our TAP program, where we have early adopters, we're actually cutting release-ready builds once a month. And we're able to do that with confidence, and that's kind of a trial run to make sure that we've got this system. So the point of all that is, yes, we're adding a bunch of new stuff, but still you can adopt it with confidence. This is also the same code tree that gets posted into SQL Azure once every other week or so. And we can't break anybody there. So there's a lot of synergies in between those two engineering environments. So what we're going to talk about is just spend a brief time on the fundamentals of in-memory OLTP, just so everybody has the common baseline to work with. First steps, what did we do in SQL 2014? So I look at this as a journey. In SQL 2014, we shipped in-memory OLTP for the first time. We targeted it at specific scenarios and made sure that we completely solved those problems. We didn't solve all problems for all people. And now, in 2016 and going beyond, we're lighting up more and more scenarios for more and more people so that we can have much broader adoption of the feature. That's kind of the way we think about this as we add functionality here. So the basics. And again, I'll go over this fairly briefly because most of you should have seen this slide. Anybody that hasn't seen this slide before? Okay. So this is just about why did we do this? Why did we think in-memory was a good idea? It wasn't because we saw it in the trade press, because we started way before that was ever there. What we did is we noticed some trends in the business and in the hardware community. In the business side, we noticed that there's a need for more and more throughput, more and more speed going through the system. People are processing more and more data all the time, and they need their database to be able to keep up with it. On the hardware side, we see some things in the CPU space and in the memory space. In the CPU space, we see the green line, which illustrates Moore's Law. All those dots are actual data points from Intel processor families. We've done the research to look at how many transistors are on each family of Intel chips. And that's where we got the data for that green line. Illustrates that Moore's Law, which is that the number of transistors as a measure of complexity doubles about every couple of years. And that continues. The dark blue line below it illustrates clock speed. So what hasn't kept up is the clock speed. You're still running about 3 gigahertz, give or take, and we have been for the last 10 years or so. So what that means is, when we take it back to the database space, is you can't count on the next generation of processors to make your single-threaded app go faster. It won't, because it's running the same speed as it was 10 years ago. But the way we're delivering the extra complexity of the processors is in terms of more and more cores per chip, right? It used to be a dual or quad core was a pretty snappy processor. Now we're talking 10, 12 cores per chip easily. So in order to take advantage of the new generations of processors, you have to have databases and your applications running much more highly parallel than they were before. So you have to have multiple threads of execution running together to make use of all those cores you're paying for now. Otherwise, if you're running just a few threads of execution, all the other cores are just sitting there burning electrons, not doing you any good. So that's one observation. The other observation was on the price of PC memory has been dropping, which isn't new. It's price of computer memory has been dropping since there's been computer memory. What's qualitatively different is the amount of memory you can get in a commodity system. The illustration I like to use is there's a machine that I spec'd out and purchased for the development group several years ago now. It's a 2-socket machine, had 256 gigs of main memory, 4 SSDs, and a bunch of spinning drives for bulk storage. And that was about a $13,000 to $15,000 machine. So if you think about getting 256 gigs of main memory to work with on a commodity box, you can do some really interesting things in that much memory. So we're not talking about million-dollar appliances here. We're talking about commodity boxes and making them screen. So that's the context. What we did with it in recognition of the fact that you can now look at having your performance-critical data at least fit in main memory is that we can do things differently. Who here thinks that in-memory OLTP is fast because the data is in memory? Nope. Because it's in memory, we can do things fundamentally differently in the engine. That's what makes it fast. You can take a system, a regular database system with on-disk tables, put a huge amount of memory at it, and you're not going to be paging data out of memory. We're going faster because we do things differently. By knowing that a table is never going to get paged out of memory, that means all the mechanism around paging data in and out of memory goes away. Pages go away. Pages are an artifact that's just there for getting data in and out of memory and tracking it. We don't use pages, so it's a much leaner data system. A row of in-memory OLTP data in memory is just that row and a little bit of housekeeping data around it. So it's much leaner. Indexes are memory pointers directly to your data in memory. So rather than going through all the machinations you go through walking B trees, each step you're decoding pages, finding your row. Now it's just following a memory pointer. It's very quick. The data is persisted on disk in a very efficient stream. So when you update one of these rows, we log it in the transaction log. We create a new version of the row, log the new version in the transaction log, and then we have a background thread that goes and harvests those new row versions from the transaction log and puts them in checkpoint files. And those are read when we start up the database, so we can get all that data loaded into memory. So again, we're just removing all the bottlenecks we possibly can. And the key point here is because we can fit a set of performance-critical data, the tables that are performance-critical, in memory, know that we're not going to have to deal with paging, we can make the whole system run a lot faster. Moving farther to make more efficient use of all the CPU cycles that we do have, we have the option of taking a stored procedure and defining it to be natively compiled. When we do that, we take the T-SQL text for the stored procedure, we run it through the SQL optimizer into the intermediate structures, then we take that, convert it into C code, run it through the Visual C compiler with its optimization, build a DLL, and load it into the engine space. So executing one of these procedures is now, instead of it being a series of interpreted T-SQL statements, which involves a lot of context swatches back and forth between threads, it's just a function called engine context. You don't even swap context within the processor. It's just way, way more efficient, way faster. There's The limitation to this is that these natively compiled procedures can only access in-memory tables. So again, a table can be either in-memory or it can be disk-based. You can have both mixed and matched in the database. Natively compiled procedures only access the in-memory tables. Non-blocking execution is a recognition of the fact that in order to take advantage of the new generations of processors, we have to have much more highly parallel, highly concurrent systems running. So in order to make efficient use of a highly concurrent system, we can't have those threads blocking each other. A typical database, if you run up a highly parallel workload against it, where you're, say, pushing data into a database with hundreds of threads, there are going to be a lot of threads that try and update the same page and get blocked against each other. So one thread gets the lock or the latch, the other threads queue up behind it, waiting for it to be done, and during that time period, all those other threads are sitting in lock or latch wait and burning electrons, doing no good for anybody. So if we can get rid of all those locks and latches, then all those threads are simultaneously making progress. You're making use of all your cores at the same time, and you're able to leverage all those cores you're paying for, right? Doesn't make sense to buy all these cores and not get any good out of them. So the more we can keep all those cores busy all the time, the more good you're getting out of them, the more performant the overall system is going to be. So again, in-memory OLTP, that part of the engine is completely lock and latch free. There are no locks, there are no latches in the in-memory OLTP engine. We do achieve full consistency, full ACID consistency, by using multi-version optimistic concurrency. That's a mouthful. What does that mean? Multi-version means, much like snapshot isolation, when you update a row, we create a new version of the row in memory. So unlike snapshot isolation, we're not keeping track of versions in tempdb and incurring all that overhead. We just create a new version of the row in memory. The rows are decorated with a timestamp of when it was created, so we know which transactions that are in flight should see which version of the row. When there's no transactions that need to see the original version of that row, we just reclaim the memory and go back to working. If there are two transactions that concurrently update the same row in memory, so one reads, the other reads, one writes, the other goes to write it back, we track the timestamp, the transactional timestamp that was read when you read the row. And when you go to put it back, we compare the timestamp you've got on your thread with the current timestamp of that row in memory. And if they don't match, that means somebody else got there first, so your update will be failed. So it's the first one to update the row succeeds. After that, they have to retry. So that's how we make sure that you don't end up with no locking and latching. You don't end up having inconsistencies where people are stepping on each other. The observation that we've made in looking lots and lots of database code is that it's really rare event for there to be an actual write-write conflict on an individual row. The other thing that makes that even more the case in this environment is that once you start executing a transaction in this environment, there's nothing that's going to stop that thread. It's going to run to completion, whether it completes in the form of a commit or a rollback, it's going to run to completion without being interrupted. Because you're never going to get stopped for an I/O schedule, and you're never going to get stopped for locks and latches. It's just going to keep running until it's done. So that dramatically shortens the time period that each transaction is active, meaning you've got a lot less opportunities for any conflicts to happen. They do happen. There are some pathological work patterns where conflicts happen over and over and over, and they're not a good candidate for this technology. We're working on solutions for them. And one example would be a work queue, where you've got you got hundreds of threads trying to pop the top element off of that, and they're all conflicting on that. That's not a good scenario for this. But overall, the vast majority of systems that we've seen do very well in this environment. And finally, it's built in. So this is just SQL Server. It's the same tools you know and love, same way of developing code, same way of accessing it, client code. In some cases, you can not even change the T-SQL code, just redefine and reload the table and keep going. Same HA and backup restore functionality works either way. So it's not a new tool set. It's not a forklift upgrade where you're changing everything. It's a very targeted change. So you find the table that is your performance bottleneck. You attack that. You convert that table and any code around that, and then remeasure your performance and see if you've solved your problems. If you have, you're done. There's no reason to invest more. If that uncovers another bottleneck, then you go after that one. This isn't a substitute for doing performance studies and benchmarks and knowing where your performance problems are. But that said, it allows you to control your investments in this transition so that you can spend as much as you want converting the specific data that you want. That's been kind of a fire hose, so let me step back and find out if there are any questions on the basics. So I need to put some nuance in that statement. There's only write-ahead logging if you choose there to be. So by default, a table is fully durable. We do use write-ahead logging. So when you create a new version of the row, it's persisted in the transaction log and then moved into the checkpoint files. You have the option of defining a table to be non-durable, so durability is schema only. In that case, we will fully persist the schema, so the table definition itself is fully durable, persisted, but the data is not. So we do 0 logging for that and 0 I/O to the checkpoint files. Why would you do that? Can anybody think of a reason? Yeah, midpoint in an ETL stream. So as long as the source isn't transient, you pull all the rows into a midpoint where you're going to do some cleansing, some reformatting, some joins, and then ship it off into a data warehouse. If that midpoint, the data were to go away, no biggie, you just start over. ASP session state cache is the canonical example. We track all the login sessions in an ASP site. If the system were to go down and come back up, that data has no value because people would have moved on and logged in again, creating new sessions. So we give the option of making those tables non-durable with the payback of having no I/O bottlenecks whatsoever. They go really fast. You don't have to take up the storage on disk. So for specific scenarios, it's lightning fast and it rocks. It's not the majority of scenarios. Our schema changes blocking. Until 2016, there haven't been schema changes. It's been drop the table and reload. We are introducing the ability to change them. And they will be blocking in most cases. Any other questions? Okay. First steps, in-memory OLTP in SQL 2014. So this is what we shipped a couple years ago when we introduced this technology to the marketplace. And again, we view this as kind of the first step of the process. So first step, we went deep. We targeted specific scenarios, mostly in-house applications where you have the freedom to change a lot of code if you need to. SQL Server 2014. So the code name for that work was Hackathon. What happens in the engineering cycles is the engineering team is usually working on a major feature area like this for a year or two before marketing decides what they're going to tell the world the name is. We have to call it something, so we come up with names. They're rarely the same as what marketing eventually decides they're going to be. So the internal name for this was Hackathon, which is Greek for 100, factor of 100, which is just an aspirational indication that we want it to go way faster. So it's released in SQL Server 2014. The value proposition for in-memory OLTP in SQL Server 2014 was Extreme OLTP performance, up to 30 times faster in specific cases. High scalability, lock and latch free architecture enables linear scaling. So if you've got huge amounts of parallelism, we can scale very parallel. And just as an aside here, that point is why it's really important to do your performance testing at scale. It's not sufficient to come up with a test harness that does a representative set of transactions but at a very small scale, because if you actually take it out to the full production workload, a lot of times there's a knee in that curve. If you don't test far enough out to where you find where the knee is, it's going to look like you're not getting any gain. But when those threads start running into each other and the latency jumps way up, we just keep going straight. And that's where you see a dramatic difference. Just a little pitch for testing at scale. It's a really hard problem to do, and it's honestly a very small number of customers that actually have a true full-scale test harness for their applications, but there's huge paybacks. Integrated into SQL Server for low TCO. So it's not a new set of tools. It's not something else you have to purchase on the side. It's not a separate install. It's part of Enterprise Edition. You install SQL Server Enterprise, you get this. It's just part of SQL Server. You know SQL Server, you know Hackathon. It's the way one of our TAP customers phrased it. Same database can host both in-memory and on-disk tables. So again, it's a targeted migration. Integrated developer and DBA experience, it's the same T-SQL syntax. Same client stack, tooling, backup restore, always on. All of that just works because it's just SQL Server. The specific scenarios that we targeted were OLTP apps with high throughput and scaling requirements. So we didn't target anything that had to do reporting workloads. There's a lot of scenarios. We didn't specifically target ISV apps that are very fixed and hard to modify. I mean, in most cases, the customers have no ability to modify them. So it was a targeted implementation for specific cases. Can you page down on that thing? So the feature set in SQL Server 2014, memory optimized tables. Durable tables by default are fully logged and persisted, so you have the full ACID characteristics of any other database. It's absolutely as secure and consistent as any other table in your SQL database. Non-durable tables as a better global temp tables in user database. There's some caveats with that we found, and that's in a lot of cases you can create a non-durable table where you might have used a temp table and get a lot of benefits because you're not incurring all the overhead of TempDB, you're not contending with it because it's in the context of the user database, you're not having to deal with locking and latching, things go really fast. The caveat is that when you define a new table, you create a new table, there's time that's spent we have to compile the access to that table. It's actually some other compiled code that we create on the fly when you create a table. That takes time. It's going to take several seconds to do that, all that definition and compilation to create a new table. If the runtime of the stored proc that's using that table is half a second, then that's a significant loss. If, on the other hand, you have a proc that runs an hour, you can gain big time from that. So you have to be judgmental in where you use this technology. I've had some customers that actually had a very highly predictable pattern where their use of temp tables always had the same schema. So they just created a standing in-memory, non-durable in-memory table within the context of the user database and used that for their temp table. And one of the primary keys was a session key, so they didn't run into each other if there were multiple executions. That was a pretty neat solution. But again, it depends on having a predictable schema. Natively compiled stored procedures contain common OLTP constructs, the basic select, insert, delete, update exception handling, and some more. Commonly used operators, built-ins, math, string identity, common query execution, joins, group bys, order bys, top, sort. You notice here there's a common thread here that is the common. So we picked the most commonly used constructs and implemented those in 2014. We didn't implement the full surface area. Again, this was intended to be a targeted implementation. Interop to access to memory optimized tables means that you don't have to use natively compiled procedures. You can just use straight T-SQL and access the tables, no problem. It's the native compilation where you have a lot more restrictions. Memory optimized table types. So again, you can go even beyond a memory non-durable table and just make a memory optimized table type, which is a very efficient way to pass in huge sets of rows to be processed in a single stored proc. So some of the results that we got. Real-world customers that were in production before we RTM'd the product. We had over 20 customers that were in production running live on this technology before we RTM'd SQL Server 2014. EdgeNet is a software as a service provider to large retailers. They host the back-end database, the product store for most of the hardware industry. So if you go to Lowe's or Home Depot, a place like that, online, the descriptions are hosted by EdgeNet. And they also host inventory data for all the stores for each of these chains. The problem that they had was when they had to update all that data, they had this massive updates of their data store, and people coming in from the web would get blocked against the locks from all those updates. They couldn't have that in business hours, so they ended up doing updates once a day at night. By moving to a memory-optimized table, they got rid of all the locking. They could do it incrementally throughout the day. The process was 7 times faster than it was on the on-disk tables. The end result is their customers now have a much better experience. Rather than finding out, did this store have this widget 24 hours ago, they find out, does the store have it now? Can I go there and buy it? Much better solution for them. bwin. bwin's a fun customer to work with because they're the only customer that's ever walked into my office and said, Kevin, I don't care what it costs. Make it go fast. Because literally, the faster they go, the more money they make. bwin is one of the world's largest online gambling concerns. They're based in Vienna. And you would not believe the number of bets people want to place in the last 20 seconds of a World Cup match. Just before they're done, it's like, I'm betting those guys are going to make it. No, he's going to make that penalty kick. So that's an incredibly compressed time frame that you have thousands of people trying to place bets. If they can't keep up with that, then that business falls on the floor. People don't make the bets. bwin doesn't make the money from that. So literally, the faster they go, the more money they make. And they had bottlenecked on their session state cache. That was limiting the amount of business they could do as a corporation. They went from 15,000 batch requests per second up to 250,000 by changing to a non-durable in-memory table for their session state cache. That's the business results you can get from this technology. Okay, I've got it. Some more customers, just letting you know that this is a technology that has really been successful in real-world applications solving business problems. IBM had 800% performance gains on the same hardware. Fusion I/O, four times performance at a 40% cost reduction. LSI, again, lots of performance gains on the same hardware. Some of the storage guys that are working on the really fast storage like it because we can push them. At this point, I'm going to hand it over to Sunil.
Okay. Thank you, Kevin. So basically what we did was, so far, we talked about 2014 in-memory OLTP customer success stories. So now we want to focus on what we are doing going forward in the next release. So we broke it down into 2 parts. One is the storage part, and one is the application surface area. And what I'm going to talk here is the storage part. So in 2014, the limitation on the durable table was per database 256 gigabyte or less. Any of you had that limitation blocked you from migration to column to in-memory OLTP? Anybody? I don't see. But there are customers who said this limitation is not acceptable to them. And why? Because they did the workload analysis and they found the performance critical tables, one or more tables, were larger than 256 gigabyte. So they could not migrate that table to in-memory OLTP because of that limitation. Now, some customers who could migrate because their current size was under 256 gigabyte, but they were worried because as their business grows, as their data grows, if they hit the limitation of 256, they will be just blocked, right? I mean, so they said, even though it works for me today, I'm getting very good performance, but I cannot really migrate to 2014 because who knows what, my data grows and then I'll be at the dead spot. So that was a key challenge. So what we are doing with 2016 is, as Kevin was pointing out, we have machines available with terabytes of physical memory available. In fact, now Windows Server will be certified with 12 terabytes, okay? So you have that kind of boxes available. So what we are doing now is we will support 2 terabytes of in-memory OLTP database size. So any customer who is running into that kind of bottleneck, all they have to do is add more physical memory and off they go. So that's one simple thing. It looks simple here, but it was very complex in terms of implementation. But the key point is we want to make sure that we can leverage the full physical memory available in the box for your OLTP scenario. All right? A question? Right. So the thing, whatever I say about the durable table applies for non-durable tables as well. The reason I hesitated, because non-durable tables do not have a storage footprint. So what you're asking is, can I have a non-durable table which is 2 gigabyte or 2 terabytes? I'm still stuck in 60s. Okay. 2 terabytes in physical memory, yeah. Okay, the next challenge. So I think, I know you guys are not excited about that, but I think it's a pretty exciting thing for some customers. The second thing, which I think was a big point of contention when people were adopting in-memory technology, was the storage. And I'll give you, do you have any idea about the storage for in-memory tables? I mean, any experience? Okay, so I'll tell you what happened. The in-memory OLTP use a very different storage model. They don't use page-based, okay? So they use something called files, and those files are called data files and delta files, the data and delta, okay? And those files are 128 megabyte in size. So what happens when you create a memory optimized table, instead of allocating a page of 8K, we allocate a file size of 128 megabyte. So what happens is when you create the database and create a simple table, the storage is large. And people say, how come the storage is so large? Okay? That is one issue. And then what happens is, as you're inserting rows and deleting rows, we do not remove the rows that you insert from that file. What we do is, we have another file which I was calling about delta files. We mark in that file that this row is deleted. Okay? So basically, imagine this. If you have 1 million rows that you inserted and you deleted all the rows, in the traditional disk-based tables, space will be nothing, will be freed up. But with the memory optimized tables, 1 million rows are inserted and we have 1 million rows marked as deleted. We'll have a key pointer to those rows. So essentially, you have no rows, but you have all that storage being consumed, right? So that's what I mean by garbage collection. So what we have in memory OLTP is these files, 128 megabyte size, they keep getting allocated. We allocate up to, in 2014, 8,000 files. That's how you get up to 256 gigabyte. So we allocate those files. But if those deleted rows are not getting garbage collected in time, what you find is that your storage has grown but number of effective rows is much, much lower. Okay? So what people had was the garbage collection is very, very slow. So I'm going to show an example. This is a detailed picture. So what you see on the left side is a green, which is the data file, which is the inserted rows, and the red file that you see, the bar, it is the deleted rows. Okay? So you can see those two guys have lot of deleted rows, right? So what we do is there's a background task in SQL Server that merges these files. So what you see here is, if I go back to the screen, what you see is that we merged these two files into this guy. So you see 200 to 400 here. It was 200 to 300 and 3 to 400, right? So we merged these guys. So the files that you see as gray files can be garbage collected, all right? Now the problem is the garbage collection was slow in 2014. So if your deletion is going on and the garbage collection is falling behind, what you will see is your storage is growing and growing and growing without the garbage collection. And the reason it was slow because we leveraged file stream implementation for data and the delta files. Now, I don't know how many of you know about file stream, but the file stream allocates files, and when those files are not needed, it does a garbage collection. So what used to happen is that in-memory OLTP, when it got the file, it loaded the rows, and when it is done, because it merged them, it became like a gray file, it used to give that file back to the file stream to say, garbage collect that. Okay? Now, file stream garbage collection was slow. It was going to take few cycles to get the garbage collection done. So what we have done in 2016 is we have decoupled the management of these files from file stream. So as soon as SQL Server knows that those files are not needed by our log transactions, we can garbage collect them. Okay? So that way what we are finding is the garbage collection of this has become much, much better. So if you have run into that kind of problem, if you use 2016, you will see the storage is not going to grow much. The garbage collection will happen much, much sooner than before. I think that'll be very useful.
So you're more aggressive on the garbage collection as well?
This is a tricky question. So we are not more aggressive. The reason, what happens is you cannot throw a file away if the log changes on that file have not been backed up and moved forward. Basically, the thing is the data, right? When you truncate a log, you truncate the log when you know that everything about those logs has been flushed to the disk. It is safe on that file, right? So we will not make that faster because that depends on the checkpoint and the transaction backup and everything else. But once we know the file is not needed, there is no garbage collection cycle that has to be done through the file stream. So we have made that part much faster. Does that answer the question? Yeah. Okay. Now the third thing was the security. Security is a big push. You saw in Sean's presentation. So the transparent data encryption is the encryption that we provided starting 2008. It provides encryption on the data at rest. Okay. So a lot of customers are using this technology successfully to safeguard their backups and everything else. In fact, the data on the disk. So the thing was, if I found some table that I can leverage within memory OLTP, and I want to move that to in-memory OLTP, the file stream on which we were basing the in-memory OLTP was not enabled for TDE. So suddenly, some data that you wanted to be secure was not secure anymore because you moved to in-memory OLTP. So it's almost like, do you want performance or do you want security? I want both, right? So that was a problem. So what we have done is now that memory optimized tables, when you create in 2016, will be encrypted using transparent data encryption. So you will not lose anything on the security and you will get the good performance. So the question then comes, what happens for my existing database, which has in-memory tables? I want them to be encrypted. So what you need to do is a little longer process. You turn off TDE, you drop the key for the encryption, create the new key, and turn it on. So that's a process. So once you do that, your existing database, when you move to SQL 2016, will be encrypted for in-memory OLTP database. Now, the final thing is actually very, very important, is the storage scaling. So as Kevin was pointing out, SQL Server 2014 was tested for scalability up to 64 cores. Okay, That's a lot of cores, okay? But now you're getting machines which are 4 sockets, 8 sockets, and hundreds of cores, right? So SQL 2014 in-memory OLTP did not scale to that level, and I'll tell you why. So this is a little busy picture, but I wanted to draw this picture to make the point clear. So what happens, what you see on the yellow strip, it are the transaction logs that are being generated by the ongoing transactions, okay? What you see, the blue is the transaction log for in-memory OLTP change, and the purple is for the disk-based tables. What I'm trying to show is that in a given database, you can have in-memory tables as well as disk-based tables, right? And you can make changes to both of them. So the transaction log is a single transaction log, it is coming, okay? Now imagine this. If you have 128 core machine, the amount of log that you can generate would be doubled, right? I mean, assuming the workload is scaling accordingly, right? So now those log records have to be persisted, right? Because we have to read those log records and update the data files and the data files. In 2014, there was one guy, single offline checkpoint thread. That guy was reading these log records and persisting them to the data files. If I have an insert, I write to the data file. If I have a delete, I write to the data file, right? That's what it was doing. So it was able to do 64 guys. But now you gave 128. So it is just saying, I can't do it, right? I mean, because it's going to slow down, which means you're going to have log growing and growing because the checkpoint guy is not able to convert that. So what we are doing now is, in 16, it's a busy picture, so be ready. We have multiple checkpoint threads. So it's not one guy anymore. I mean, there are multiple checkpoint threads. And essentially what you see is, I'm showing you 3 threads here. So basically, like multiple checkpoint threads are going to write. So essentially what happens now is you go to 128 core machine or even 256 core machine, they are creating 4 times more log, right? But there are 4 times more threads to do that. So with that, what we are finding is that we are able to scale for the workload on those big boxes, okay? Now, just 1 second. The offline checkpoint thread that I'm talking about here, it is currently 1 thread per container. Now, what is a container? Container is a concept from file stream. So if you have, say, 4 containers, almost think 4 containers means 4 disk drives. So we will have 1 thread per container. So essentially, that's how you can determine how many offline checkpoint threads you need, and you can and do that. So there was a question here. Sorry, ask me.
The log file is usually 1, and it's usually on single disk.
Right.
So how many checkpoint threads will run on that?
Right. So I think the question really is that now that log, there are multiple threads that are reading from the log, right? So in a truly well-configured system, the log will be in memory. So these threads will be reading the log from the memory. So there is no disk, right? What happens if suppose offline checkpoint thread falls behind, that log space will get full, it will get flushed to the disk. In fact, what happens is, it's like a snowball, right? If you're falling behind, the log goes to the disk. Now the offline checkpoint has to read from the disk and then write it, right? But if everything is keeping up, they're reading from the memory, right? So that's pretty much all we have done. I just want to summarize. Number 1, 2 terabyte. We are targeting the full physical box capacity for in-memory OLTP. Big thing for us. Garbage collection storage is much more streamlined. And then it is scaling to the big boxes that we have. So with that, I'll hand over to Kevin.
So Sunil has been talking about the changes that we made in the product in terms of making it scale to bigger and bigger data sets, being able to keep up with faster workloads on the back end, all the little bit housekeeping that we have to do in order to keep up with things, making all that work more smoothly and more efficiently. I'm going to talk a bit about increasing compatibility. I talked initially about the fact that the surface area we exposed in SQL 2014 was commonly used constructs. We're greatly enhancing the number of those constructs that we'll support, making them much able to handle a lot better set of situations. We see some challenges in applications, especially when we're working with SQL 2014 with in-memory OLTP because there was no ability to change data in place. You just dropped a table and recreated it. So if you have ongoing active application development, you don't want to tear down your test data set every time you change the schema definition. That's really a pain. You may have agile iterative development methods where you're changing your environment with each sprint. And some of those changes means changing schema. If you're then again having to drop your data and recreate it, that's really painful. Tuning your application and database. So that may mean changing the indexes, may mean changing bucket counts on hash indexes. All those things were really challenging in SQL 2014, responding to shifting data patterns. And ultimately, just the need to modify the database schema without dropping and recreating your whole database were really painful. And we recognized that, and that was one of the limitations that was really high on the list to get out from under. So, there. We will be supporting alter in SQL 2016. Hit it. So alter procedures and SP recompile are supported fully online. So if there's a thread executing the original procedure, it will finish that to completion while we're compiling the new version. As soon as the new version is done, any new threads will pick up the new version. So it's a fully online change there. Alter table for schema and index changes, and for schema and index changes, it's an offline, being that we're behind the scenes having to make multiple copies and shuffle data, but we're doing all that for you, so you don't have to. Full schema change support, add, drop, alter column constraints. Index operations, add and drop indexes. So you now don't have to define every index you might possibly use up front. You can add indexes when you find out that you forgot to create an index on a certain key column. Change hash index bucket counts. Who here that has played with in-memory OLTP has been bit by having the bucket count the wrong size? It can be really painful if you way undersize your bucket count. And in 2014, in order to get out from under that, you have to unload all your data, drop the table, recreate it with a better bucket count, and then load your data back in, and then get back on the air. That's some downtime. New syntax is alter table, add, drop, alter index. Alter table is an offline operation, and it will require double the memory just for that window when we've got both copies of the table stood up before we can delete the old copy. We do not yet support SP rename. That is on our roadmap. That would enable you to create a new copy and just rename behind the scenes. So I'm going to show you what this looks like on a live data. So on this laptop, I have two instances running. One is running an early build of CTB2 for SQL Server 2016. This is not fully baked. It's going to be a little bit yet before we release 2016 CTB2. It's coming soon, but it's not quite baked yet. But that's what I'm running here. So I'm going to create a fresh database, add the memory optimized data file group to it. Can add a container to store the checkpoint files, the data and delta files. Going to create a trivial table that has an identity column for the primary key, date time column, and then just an int column. And who can see what's wrong with that table definition? What was that? Bucket count. Bucket count of 20. Is that likely to be a successful table? So for those of you that haven't been bit by this, what happens when the bucket count is too small? The bucket count defines the size of the array of in-memory pointers for a hash index. So we'll hash into one of those buckets, and that's the pointer to the first row. If you have too few buckets, that means there's going to be a lot of hash collisions. So a lot of different rows are going to hash to the same bucket, and that means we'll go to the first one, and then we have to go to the next and follow these chains until you actually get to the row you're looking at. And that can slow both inserts and selects down significantly. So that's why a bad bucket count's a bad thing. So we created that. Now I'm going to create a native proc to load a bunch of data. I've got a loop that'll load 100,000 rows into that table, putting a random value for the int field. Execute it. It takes a couple seconds. So again, this is for each row, we get a random value in the range of 1 to 10K, 1 to 1K for the int column. It's done. That was 100,000 rows. And again, we do have that number of rows. Select a random row. So this is a very useful DMV to use. DMXTP hash index stats. This is how you can find out how healthy your hash indexes are. So what you see here, these two columns are really bad news. So your average chain length, so the average length of hash collision chains is over 3,000 long. You don't want it anywhere near that long. If I had loaded a full data set, if I didn't have this running on a laptop, I could have loaded millions of rows. That would be even significantly longer. Max chain is 3,100. Empty bucket count. So in a healthy hash index, you would have some empty buckets. So you're not completely all filled up. So now comes the new stuff. Now we're going to alter that table, alter the index for the sales order hash index, rebuild with bucket count equals 400,000. Just that fast. And now we look at the hash index stats for the index after we fixed it. The maximum chain length is 4. Average chain length is 1. That's a really healthy hash index. This is a really useful DMV to use when you're monitoring the performance of an in-memory OLTP system. Lots of empty bucket counts, so lots of headroom there. Question? We don't. Total bucket count is 500,000. So the bucket count that we create is always going to be a power of 2. So we'll round it up to the next higher power of 2. That's why originally, if you look close, you saw the buckets in the first index were 32. That's the next power of 2 up from 20. If I was being a little bit more disciplined, I would have put the power of 2 into that, so there wouldn't have been that discrepancy.
Right. I think one thing I want to add is, if you wanted to change the bucket count in 2014, you had to move the rows out to some other table, a very painful operation.
Okay, so another challenge is writing queries that might have to do reporting style queries against an in-memory table. And the reason that was challenging is in SQL Server 2014, queries against in-memory OLTP tables, again, were optimized for OLTP transactions. That's typically single thread, single row lookups, and that's what they were. The original target space, the confined targets, was that scenario. But if you do have to run a report that scans a lot of tables, if you're joining against a column store for some report, the queries for in-memory OLTP tables are run at a DOP of 1 in SQL Server 2014. So no matter what else you're doing, if that query touches a memory-optimized table, your query is running at a DOP of 1. So one of our early thoughts had been, great, we can have a memory-optimized table and a column store, and we'll join them together and life will be good. No, it sucked, because column stores really depend on high degrees of parallelism, and you lose all that because everything runs at a DOP of 1 when you're touching an in-memory table. SQL Server 2016 now enables queries to touch in-memory tables and use fully parallel plans, and I'm going to show you what that looks like. So I have actually two instances. One is running SQL 2014. That's the one I've just switched to. And again, you see edit version. This has the same table, same schema, same data set, just running on the different version of SQL. I've turned on the actual execution plans, so we'll find out how this query is being run. So this is doing the average number within that randomly generated column. So you see that this is a index scan. There's no parallelism in this plan anywhere. So it's just a single-threaded scan of all that data. Not too painful in a small table, but it gets pretty painful on a very large one. If we flip over to the 2016 instance and run the same query against pretty close to the same data. Yep. And look at the execution plan for that one. Grab it. There we go. That's not supposed to happen. Go away. So now you see all those parallel operators that have the double arrow. Those indicate parallel operations. So the scan, the aggregate, parallelism, gather, those are all parallel operations, showing that just by running on the new version of the SQL Server engine, we're getting now parallel execution out of the plan.
Right. And this is critical for operational analytics as well, because you want to run your analytics in parallel, and that is enabled by this.
Any questions on that so far? No, pretty straightforward.
Right. So this is a great question. All optimizations that are available for column store on disk-based tables are available on column store on in-memory tables.
There was no batch mode here because it wasn't a column store. So if there had been a column store involved,
That's right.
then the column store could have run in batch mode.
Correct. I didn't notice that. Okay.
So converting existing applications, particularly if you've got some interesting constructs that might not have been supported before. So we have some of the outer joins that hadn't been supported in 2014 are now supported. Disjunctions or not. Union all. Select distinct. Subqueries. So again, we're getting beyond just the core basics of T-SQL and rounding out the surface area much more. Foreign key constraints and check constraints are now supported on in-memory tables. Anybody happy about that? So I got a lot of feedback about foreign key constraints missing in 2014. We fixed it. Unique constraints and indexes. Natively compiled procedures, nested stored procedures. So one of the things that ended up being really painful in converting applications was that we didn't allow you to nest stored procedures. So you couldn't call one stored procedure from another. It didn't seem like a big deal at the time. What ended up happening is you find a really substantial applications has done some refactoring, so you don't have duplicated code all over the place, right? You have specific stored procs that do specific work, and they get called from other stored procs. In order to convert something like that in SQL Server 2014, you end up inlining all that code, and you turn up a few hundred lines of T-SQL into thousands of lines, and it's just ugly. Now we support nested stored procedures. Natively compiled scalar UDFs, indexes on nullable columns. That was a pain as well, because in 2014, you couldn't have an index on a column that was nullable, because we had to have a value there in order to place it correctly. Now we're able to handle that, so you can have optimized index seeks on tables that have nulls in their definitions.
Sorry, that's working too. Okay.
Custom validations, again, DML triggers on memory optimized tables. So if you have an application that does data validation in the fly, you want to, when you change data, you want to validate it using a DML trigger, we can now do that. A lot of entity framework generated code and ISV apps use Mars. And they're not the exclusive users of that, but they're very commonly use that. If you use entity framework to do code first, they're going to set up your connection string with Mars turned on, regardless. In 2014, we couldn't support a Mars, so that was a problem. You had to go tweak the connection string and hope that didn't break anything, or just not use it. So now we do support Mars fully. Table Designer is supported in Management Studio. For migration and manageability, we've worked on the tooling a lot. So we have assisted migration for stored procedures. This is an evolution of the AMR tool set that was in 2014. We've made it a lot more lightweight on the data gathering part and a lot more helpful in terms of assisting migrations. Best practices analyzer support. Who here had problems with collations in SQL Server 2014? We now will be supporting the full range of collations. Non-Latin code pages for varchar and char columns. Non-bin2 collations for comparison and sorting, indexes, all that will be lit up in this version. Increasing platform abilities. So what do I mean by that? I mean that this isn't restricted to on-premise box product. We're merging the feature sets between the Azure SQL DB platform and the on-premise platform. Those are getting closer all the time. This is an example of that. We have a private preview active now that enables in-memory OLTP in Azure DB. So it's in the V12 SKU, internally we call that Sterling. You'll be able to do full hackathon in-memory tables in a SQL Azure DB. There'll be a public preview during the summer, so anybody that wants can just pull up and access it, and then eventually it'll go GA. So you may have seen this slide in the foundation session. This is talking about operational analytics. Sunil, you want to talk about this one?
Okay,
That's
I can.
baby.
So traditionally, the way people do analytics on their operational data is they ETL the data out from the operational system into a data warehouse, and then they do the analytics on it. So what we are providing, this is a significant change that we are adding to SQL Server, is okay, so this is a slide actually I have not talked before. So basic thing is, if you were using this technology where you ETL the data out, load into a warehouse, and you want to do for fraud detection, right? You will not be able to respond in a timely fashion because ETL is happening, say, every day or every hour, so you are behind, and you need to be ahead of the fraud detection in this case, right? So what we are providing with the operational analytics is that you do analytics on the same schema, same tables as your operational data, right? So in this case, what we are showing is that you have your in-memory table, and you create a column stored index on it. This is something that we are providing not only for in-memory tables, we are providing for disk-based tables. You create a non-cluster column stored index on it, which is updatable, And now you can do both OLTP as well as analytics at the same time. So in the fraud detection scenario, somebody is trying to make a transaction, you can do analytics on it to figure out whether the transaction was a fraud transaction or not. So that is a capability that we are providing with in real time. And as I said, this is available both for in-memory OLTP as well as disk-based tables.
So in the past, where you would have gotten the data into a column store or data warehouse format, so you could do the analytics queries to find out if there was something that should trip flags that might be fraud. That was at the end of an ETL cycle, which may have been hours, minutes, hours, days. If we're talking about something like credit card fraud, they're gone, right? They've got your money, they're gone by then. And if you're Visa, you're probably picking up the tab for that. So by having it all active on the same data set at the same time, we can now do that inline in real time. So there are actually some credit companies that are doing this level of analytics in line with your credit card authorization if it's a significant amount. So that's major enhancement in major business results again.
Correct.
So that's a quick tour through SQL Server 2016, what we're doing with in-memory OLTP.
Lob support.
So we're also looking to support LOBs in 2016, which wasn't in 2014. That's still being worked on. It's not in the bits that you'll see in a month or so, but it is coming. Victor.
If I want to take advantage of UDFs
Mm-hmm.
and non-durable tables, will I be able to enable Hekaton at the database but not have the file stream containers and the checkball files being generated?
At this point, you have to have the memory optimized file group. We've dramatically reduced the footprint of the files that get created, but you do have to have that. That's topic of a lot of long conversations. Any other questions?
General question not related specifically to this. Is there any value to reorganizing or rebuilding the indexes with fragmentation now if they're on a SAN that's got physically fragmented anyway?
There is, because what happens in SQL Server, fragmented index means that the rows are logically out of order. And that means if we're here and trying to do a scan, we do read ahead to try and get the next rows, but the next row logically is behind us. So the read ahead doesn't work that way. So that's why it does make a difference, even if you're on a SAN. So it's not physical fragmentation that we're talking about, it's logical fragmentation within the indexes.
Does it influence optimization we have?
No, it doesn't.
Fragmentation, the cluster ratio doesn't influence the optimizing choices when it's picking.
Yep. Yes?
Is there been any kind of optimized for a certain size of table? So when you create the table, rather than specifying a bucket count or having a property before it say optimize for say a billion rows, and therefore it would then work out what a good bucket count size would be relative to your target size of the table.
So the question is there a way to optimize for a certain cardinality on the table? But that's what the bucket count is. It's
I guess my point is that you're by trying to guide someone to creating a better bucket count in the first place by them telling you how big the table in their intent is, so that then you can then infer that and then be able to give them a good bucket count.
Right.
That would be an interesting advisor to create. What really matters isn't the actual number of rows, but the number of distinct key values. So if you've got a true-false column, you're only going to ever have two values. It doesn't matter how many more buckets you create. They'll all be empty. That's an extreme example, of course. But I take your point that it would be good to have some guidance, some tooling that would help guide people through that, help make them more success-prone.
Are there a lot of vendors that are adopting or supporting the use of these, including Microsoft?
There are vendors that are starting to more. Again, the target for 2014 was not ISV apps, and so the ISVs that tried that, a few of them were successful, most of them weren't. We're working more aggressively with them. We have the Dynamics applications we're working very closely with. They'll be adopting some form of this. Several of the other properties we're also working with, as well as a number of external ISVs. Those are a prime target for this release.
Yeah, we are seeing the traction, but I think the key challenge was the surface area limitations blocked a lot of people. And our goal is to unblock them with this incremental release that we're doing. Yep.
So when you implemented parallelism in 2016, if your database is tuned or maximum cost of parallelism is already set, how does that affect the rest of your maximum cost of parallelism?
I didn't hear all that.
Can you repeat the question, please?
Yeah, so if you, right now our system is set up, the way I have it tuned is my max stop is set, my maximum cost of parallelism is set based on research and knowing our workload. If we move to some in-memory tables, what other things do I need to continue to look at to retune those?
Right, right. I think so. You're talking about the parallelism threshold, that percentage is, yeah, okay. Right. So I don't have a good idea what we should do. It's a good feedback because now we have parallel plan for in-memory. So we need to think about what recommendation should be. So I think we'll take that as a feedback.
That'll be a blog post. But primarily,
But
what you're
needs
looking
to do black, yeah.
what you're looking at is now the in-memory tables can take advantage of that tuning you've already done. And as a first order approximation, that's probably going to be a lot better than one.
That's right. Yeah, I agree.
Does this work in similar way with always on read-only replicas in memory table?
So the question was, does this work in the same way with always-on read-only replicas?
So parallel queries.
Parallel
That's what
queries,
I-
yeah.
Yeah, yes.
So readable secondaries are available in always-on. With 2016, we'll round robin across the readable secondaries, and we'll use parallel plans on a query on a in-memory table, whether it's read-only or not.
Yeah, just to follow up that other question. When you adopt the online tables, the LTP vehicles, are there different sets of weights that you should be aware of? You know, for instance, you mentioned TX packet weights. Would you be unduly influencing the number of TX packet weights with trivial packet weights because they're all random? You know, are you going to augment your stats and you have to just be aware of that versus your historical model?
So I think if you're talking about CX packet weights, I mean, CX packet is a CX packet. I,
There's certainly a lot. There's certainly a lot of different telemetry you're going to be looking at for in-memory tables versus on disk. There's different typical bottlenecks that you're going to run into, different things you're going to watch. We've given you a lot of more telemetry that is specific to these tables, like the hash index stats DMV that I showed you. And I'm sure we'll have their white papers out there already. There will be more coming with 2014 as we open up the surface area that help guide you through that. Any other questions? One more.
What changes do you see, how do you see this technology being implemented with Dynamics AX?
so the Dynamics AX, as you know, is a ERP application, right? So the challenge is some of the code in the Dynamics AX application depends on blocking. Because Hackathon or in-memory OLTP provides non-blocking implementation, so the amount of changes they have to make, they are still evaluating, but it is significant changes. That's one. However, for their operational part, for their analytics part, they are considering column store technology. So Hackathon is, at least for the application that I'm working with them, is not on the cards, but they're going to look at the column store.
They've done some prototyping on the operational analytics idea where they could get away from the whole ETL cycle and dramatically collapse the time to get to those analytics. So that's
Right.
another possibility. One more question, then it's...
If you're targeting ISVs, is there an implication then that you'll
So the question was, if we're targeting ISVs, does that mean we're targeting standard? Not at this time. Again, ISVs are kind of a proxy for applications where we desire not to have to refactor a whole lot of code. That's not a decision I get to make. Okay? We'll be around for a little bit, but thank you.
Thanks a lot.